able to resolve. That's why today, half an hour earlier only, I have logged in.
Okay, okay.
Anyways,
Yeah, so like in yesterday's session, we had discussed one example related to basically using MATLAB. So I can like just share my screen. I'll just share my screen.
those sessions have been recorded, na? If they are recorded, then I will.
Yes, yes, yes. Yesterday's session was also recorded. I have uploaded the link to in the weekly log, that weekly sheet that
Okay.
we uh, generally follow for. So that you will get the link to yesterday's session also in that.
Okay.
So in yesterday's session, I was discussing, like I just gave an overview of whatever content that has been covered overall in this course till now, and then uh, we have like these we have discussed, like in week 7 content there was like mention about using Simulink for different kinds solving different kinds of problems. Look, like uh, so there was an example of simple pendulum
Yeah.
using Simulink. So we had actually covered that example in the last 7th week's usual session, and we also discussed how to use Simulink as well as Simscape for the solving like a simple spring mass damper kind of a problem. Uh, but like that was mainly focused on Simulink. But now it is not necessary always that we should use Simulink for solving these modeling and simulation problems. So we can also use just simple MATLAB code also for modeling and simulation. So to demonstrate that, I had selected this example of this same simple pendulum.
Yeah.
So we can solve
It
that
is.
same. Yes,
I unfortunately. So what I matlab, aim is that ki one can reach this files and generate the output. I do have a MATLAB and
okay.
also try out clear my concepts by utilizing it and playing with it. I will see.
Yeah, yeah. So yesterday I had demonstrated that we can also solve the same simple pendulum problem using just simple MATLAB code also. So I can just quickly go through that also again if you want. So do you want me to go through that example?
Yeah, please. Yeah, till the time others join, I think it will be better.
Sure, sure. Yeah, so in this simple pendulum example, uh, using MATLAB code, we can use the same ODE45 solver. So which is there, like the same solver, we have it in Simulink as well. But here we have to provide the input slightly in a different way. Uh, so first of all, we have to define the input parameters. So in case of the simple pendulum, it will be mainly just the length of the pendulum and acceleration due to gravity.
Yeah,
If we neglect any damping or anything like that, so then there will be just the length and the acceleration due to gravity. Those will be the only parameters required. And the initial conditions, which are basically the initial angular velocity and initial angular position. So here we assume that we release the pendulum from a certain initial angular position with zero angular velocity, and then allow the pendulum to oscillate. And then we have to define the time span over which we want the solver to solve that differential equation. So then we define that time span as a two element vector over here, and then y0, that is the set of initial conditions that we will give to the solver. So the solver we are using is OD45. So it uses a combination of fourth order and fifth order Rangakutta numerical method. So for numerical integration of differential equations.
Yeah.
So this solver by default it requires the like this is the syntax. Like by default we need to provide the uh, like function handle to the set of the differential equations that we want to solve, and those differential equations should be in the state space kind of form, and the next input is basically the time span, and the third is basically the initial conditions. So now if we want to look at the differential equations, so let me just open up. So are you able to view my are you able to see my PowerPoint screen?
Yeah, 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 visible.
Yes. So this is the differential equation that we get for the simple pendulum, and then we convert this second order differential equation into a system of two first order differential equations by introducing the substitution that theta dot is equal to s. Then s dot, which is basically derivative of s with respect to time, will be equal to theta double dot. So then the second differential equation we can write it as s dot is equal to minus g by l sine theta. So this is how we can convert the second order differential equation into a system of two first order differential equations. So this is also called the state space form. So it basically it's in the form of like let us say z dot is equal to f of z, some function of z. So that kind of a form. So uh, we need to construct the function. We need to write basically the function in MATLAB in which, so here the name of that function I have given as simple pendulum ODE. By default it should take the inputs as time and the current state vector x. So the state vector x will be here theta and theta dot. So it's a vector of theta and theta dot. And there are additional parameters which are basically g and l which we are passing to the function, and it should provide the output x dot, which is basically the time derivative of the state variables, which is basically theta dot and theta double dot. So we are basically here writing essentially the same differential equations here. So the first differential equation is theta dot is equal to s. So theta dot is basically the time derivative, and s is basically x. The in the state vector x it is the second element. So then therefore the first row of this x dot will be x of 2, which is the second element of x, and the second row is basically s dot is minus g by l sine theta. So theta is basically the first element of x, which is basically x of 1. So therefore we write it as minus g by l sine x of 1. And so this is our state space form of differential equations, and we have to give it to the solver, and here we are constructing the function handle. So here we say at t comma x, so by which the MATLAB can understand that it is uh, the function has the function is accepting t and x as the time varying inputs, and then g and l are basically additional parameters that we are passing. So while solving, it will pass the parameters g and l and solve for t and x. So this ODE fun whatever we have written, so that is the function handle, and then time span and y naught. So and the outputs are basically the time vector and y. So t and y means basically uh, it gives us the time and the solution in the form of like the uh, the values of theta versus time and theta dot versus time. Basically the two states. So those we get as the output. Now to compare like this, so we generally consider this analytical solution by considering the small angle approximation, so that so we consider sine theta is nearly equal to theta. So therefore in that differential equations it will reduce to theta double dot is equal to minus g by l theta. So then uh, it is like the second order differential equation with constant coefficients. So then it will have a simple sinusoidal kind of solution like a cos omega t plus b sin omega t kind of form. So the natural frequency omega n is square root of g by l in the analytical solution. And then we can write the expression for the angular velocity and angular position with respect to time using this analytical solution for the same set of initial conditions that we are considering for the ODE 45 solution. So using the initial conditions, we can derive it to be of this form theta naught cos omega t, and then its derivative will be minus omega n theta naught sin omega nt. So we basically store the values of the analytical solution and then we plot them together in the same axis so that we can compare how this small angle approximation holds with respect to the different set of initial conditions. So let us say we consider to start with, let us consider that we displace the pendulum initially at an angle of 10 degree and release it, and let us see how the solution looks like. So we can see that the solution that we get using ODE 45 and the analytical solution are very close, and it is approximately or like more or less sinusoidal kind of a behavior with constant time period. But now as we increase the initial angle by which we displace the pendulum, let us see what happens now. So now we see that the solution that we get using ODE 45 deviates from the analytical solution, and if we go on increasing the initial angle, we will see that the analytical solution no longer holds good. So the time period is actually not constant with increasing with increasing time. If we put minus 60 degree, then we see that for let us say for the initial 2-3 seconds it's the analytical solution and OD45 are close, but then they start deviating. But interestingly, near time 30 seconds, again the analytical and OD45 solution are coming close. So basically in so the numerical solution does not give us a sinusoidal kind of a nature with constant time period. So this is the this is an important thing, that the utility of this uh, analytical like the numerical solution that we have. So there are some other problems which where we can derive analytical solutions. So we can use this as a tool to compare between the numerical and analytical solution in this way. But for other problems where we do not have any analytical solution, then this is the only way we can solve these problems, by numerically integrating the differential equations. So this was the problem that I had discussed yesterday. So were you able to follow?
Yeah.
Yeah. Then another example that was discussed is that if we have a pendulum which is hitting a wall now. So there is a wall at certain angle, and then uh, if we release the pendulum from a certain angle and then allow it to oscillate. Now then, if we provide an enough initial angle to it so that it will definitely hit the wall. So then how do we solve that problem now using MATLAB? So that was what we had introduced the discussion yesterday. So anyone has any idea how do we solve this problem?
Do you put a constraint saying if the angle is greater than certain angle, take a zero or reverse it?
Yes, yes. In Yeah, you are right. So what we can do is we can identify the point, the the time instant at which the pendulum hits the wall, and so till that point the pendulum is still just freely moving just before it hits the wall. So the same differential equation for the pendulum is valid. So then up to that time instant we can get the solution to the differential equation using that ODE 45. And then there will be a collision. So let us say, depending on the nature of the collision, so if the collision is purely elastic, then the ball, whatever that pendulum bob, will bounce back with the same velocity. But if the collision is inelastic or partially inelastic, then it will lose some kinetic energy. So then it will bounce back with a slightly lower velocity. So then to model that, we introduce the coefficient of restitution in that, to basically, so the momentum, the initial momentum and the final momentum, they will be related by the coefficient of restitution. So now since the wall is stationary, there will be basically just a change in sign of the velocity of the pendulum bob, and some reduction in the velocity. So that will be as per the coefficient of restitution. So then,
Sir,
yes.
one question. Sorry to interrupt. Is it a requirement of MATLAB that you get a S dot, S and S dot instead of just going ahead with theta dot, and theta?
No, 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 there is no such necessity. It is just to demonstrate that how we split the differential equation. So it's basically uh, the first differential equation is this theta dot is S, and the other one is this thing. So if you can just directly write down the state space form, then on your own, so then that is fine.
Okay.
But uh, it's basically just to illustrate how we split the second order differential equation into two first order ones.
Okay.
Yeah. Yeah, so then in this problem, so any one of you are aware of the events function from that feature in MATLAB which we have in these solvers? Anyone has any idea about that?
No, sir.
Yeah, so basically we can track some event, uh, like some phenomenon, event based on the nature of the state variable. So, like if let us say now in this case, we can keep track of the event that when the pendulum, the angle made by the pendulum with the vertical is equal to the angle made by the wall with the vertical. So we can keep track of that event, and the instant at which this event occurs, we can tell the solver to terminate its execution and then collect the solution up to that time instant. Then introduce the effect of the collision, and then just after the collision we know what will be the uh, initial, like the angular position and the angular velocity. So it will be basically just the reversal of the sign and then some reduction in magnitude if the coefficient of restitution is less than 1. And with those now updated initial conditions, we can again start the solver again, uh, and allow it to solve till it comes back again. So till it reaches its maximum position of the pendulum and again comes back to the wall and up to the next collision basically. So the time between collisions we can use the same, like the solver to integrate this differential equation and keep track of the collision event. So keep track of the time instant at which the collision happens, and then collect the piecewise solution and then combine them together to get the complete solution with respect to time. So that kind of an approach we can take. So I'll just uh, explain the code that I had for this. So any questions or any doubts regarding this?
No, but here these so that we can check around it and try different permutations and combinations to understand the concept, nothing else.
Sorry, I did not get your comments. Sorry.
I was saying you can share those .m files so
Haha.
that go ahead and we can check around with it and understand the concept by putting different parameters to it.
Yeah, yeah, sure, sure, sure.
Thank you. So we are going to last assignment.
Sorry, I didn't. What were you saying?
Now we are going with last assignment.
Yes. So this is just an demonstration which I wanted to give, like which might be helpful from MATLAB, like using MATLAB for problem solving.
Yeah,
We will also be discussing some examples related which are similar to assignments in this session.
fine.
Yeah. Yeah. So I'll just explain the code that we have here. So here we consider the coefficient of restitution E as 0.8 and we assume that there is no damping present in the system. We can introduce damping in the system by tweaking this parameter C. So that is basically viscous damping constant. And then we take the set of initial conditions theta I and the initial velocity and the initial angular position, and then we define the initial, like the position of the wall, and we say that we want the simulation time to be 30 seconds. Then we actually go to the OD45 solver. So there we use this events functionality, so where we detect the event at which basically so we write an event function which will take the time and the state variable vector values. So y, the state vector y will contain basically theta and theta dot. So the value, uh, in this case the value variable will contain the difference between this the instantaneous angle minus the angle made by the wall. So the time instant at which this value variable becomes 0, we will say is terminal is equal to 1. So that means that it will terminate the execution of the solver. So, and this direction is basically whether we want approach the zero value from either. So we can we tell the solver to that we can approach it in either direction. So not necessary from positive or negative direction, whichever direction it is possible. So uh, and then so you can read more about this events functionality. So there is I have also provided a link to the documentation, or you can just say. So in these options that we pass to the solver, so there is this documentation page on ODE event location. So you can go through this documentation to read to know more about this feature, so which we are using in this example. So as I mentioned, so we construct a while loop and continue its execution till the final simulation time is reached, and and in each iteration of the loop we basically solve from the initial time instant up to the time instant at which the pendulum hits the wall, and then we set the new modified initial conditions after the impact. So the theta value will be the same, just at the as the the same as the location of the wall, and the velocity will be basically the coefficient of restitution multiplied by the earlier velocity, and with the sign reversed. And we note the time instant at which the impact happens, and the while loop is checking that the time at which contact happens is less than the final simulation time that we have set. So it will store the solution that we have obtained till the impact time in this t vector and y vector, and it will keep repeating this while loop till the final simulation time is reached. So uh, so this is how we can use this concept, and then we can plot the displacement and like angular displacement and angular velocity. So let us say if we start with an initial angle of minus 150 degree. So minus 150 because it is like in the clockwise sense with respect to the vertical axis, and then release it, and the angle at of the wall is at 40 degrees, so it will uh, go and hit at 40 degrees, and then since we have assumed the coefficient of restitution as 0 0.8, here we can see that the angular velocity, there is an instantaneous reversal in the sign, but a slight change in the magnitude of the angular velocity. So in each impact it will lose some kinetic energy, so then it will come back to a lesser lesser and lesser maximum angular position, and finally it will reach an angular position such that it will almost like not hit the wall at all. Like if we solve for a long enough time, let us say if we set the simulation time to 60 seconds or so, we will see that the amplitude of the pendulum will essentially remain constant after a certain time, because so we can see it is oscillating between plus or minus 40 degree angle. So uh, so then that means that the pendulum will just barely reach the wall and then come back. So there is no actual collision that is happening after that time instant. So because there is no damping that we have assumed, so therefore there will be no further reduction in the amplitude. But if we assume damping, then it will like it will not hit the wall at all after some time, and it will also continuously keep losing its amplitude. So that is how we can use MATLAB here to simulate the behavior of such problems, where we use this functionality of events. So were you able to follow this
Yeah.
example? Okay.
Also wanted to know, do you have anything regarding Simscape done in any kind of example where you can simulate things and also get the results what you shown just now, but also understand what will be it depicted graphically oblique simulation, what kind of thing it will come out.
Yes, we had discussed actually an example using Simscape, like the simple spring mass damper kind of a system. Uh, how we can create a physical model of it, and then similarly also create the model of the same system in using Simulink and get the same output. So we had discussed that. So I think it's there in the week 7 lecture recording, so you can go through that. Right now I do not have a another example of Simscape available with me right now. So I think you can go through the recording for the 7th week session. That would be helpful. Does that answer your question?
Yeah. Thank you so much. Yeah.
Sure. Yeah. Okay. Fine. So anyone else has any other questions or comments?
Sir, I have a few questions, sir.
Yes.
In week 2 of the lectures,
Uh-huh.
sir has shown that inductor is equivalent to mass,
Mm-hmm.
and then capacitor is equivalent to spring.
Okay.
That was in lecture number 6.
Okay.
But when it come to week number lecture number 12,
Uh-huh.
there was a slide showing the reverse. Like inductor is a spring and capacitor is a mass. I'm not sure under what situations does this changeover take place. I have sent an email with the photographs to the forum. You
Okay.
can watch it, you will be able to see the slides.
Just let me check. Just so you were saying in week 2. Uh,
No, yesterday or today, I've sent two emails. And another question I wanted to understand is when we talk of energy, we write half mv square as a kinetic energy and potential energy of a spring as a half cv square,
mm-hmm.
half kx square, half kx square.
Kx squared. Huh?
Yeah, but when it comes for power dissipation, we are writing it as without that half.
Uh,
I don't know why
Power
that half.
dissipation without half in the sense.
When you see the kinetic energy, we write half mv square, right?
Yes. Yes. Yes.
That has an half factor in the beginning.
Mm-hmm.
Similarly, potential energy has a half kx square.
Yes.
Whereas when it comes for dissipation, they are just writing cv square without that half. Instead of half
Ha, ha,
cv
ha.
square. Why is
No.
that, Jude?
See, the power dissipation, like that half factor comes out as like when we integrate, work done, like work done by a constant force over a certain, like or like not constant force, but like uh,
I understand
so
why half is coming
yeah,
in kinetic energy and potential energy.
yeah, exactly.
That
So
because of integration it is coming.
yeah,
Why
exactly.
in power dissipation we are not doing the integration?
So it's a different quantity itself, basically power dissipation. Uh, so power dissipation, it's proportion. If it is proportional to velocity, then it will be some cv, and if it is proportional to the square of velocity, then we will say it is cv square. Half factor, it's like it's not necessary in that case because there we are just saying that it is the constant of proportionality is, let us say, c. So half c will be again some other proportionality constant, we can call it as b. Then we can also write it as bv square, where b is equal to c by 2. So that half factor is actually not required in that case. So it's like basically just showing that the force of, like, dissipating force is proportional to velocity or proportional to the square of velocity, or like whatever, like that.
Okay.
Okay.
I'm not sure that that was a typo error or there was a different situation where inductor will be treated as a spring and capacitor will be treated as a mass. But the slides shown were in that fashion.
Okay. I think I'll need to check that those slides, and maybe I'll let you know in the discussion forum. Like,
Okay.
yeah. Okay, fine. So, so I had picked up some problems which are similar to the kind of assignment problems in week 8. So we can discuss those.
Okay, sir.
Yeah.
Yeah, please go ahead.
So just let me just share my screen. Just wait for a moment. Just please give me a minute to pull up the questions. So I am sharing my screen now. So is that visible? The questions?
Yeah, it is.
Okay. So let us get started with the questions. So the first question is parameter estimation method is used to define what? So what do you think?
C,
Sorry?
C, model parameters.
Yes, it is right. It is model parameters. So the parameter estimation is uh, used to derive the model parameters. Like if we have a certain input output um, set of values, then we can fit a linear regression relation to get the model parameters. Now here we have a question where we have to estimate the parameters a and b using the least square method for the model y is equal to a plus bx. So we have three equations. So basically we have set of three y values and three x values, and we need to get the uh, parameters a and b. So I'll give you like 2 minutes to think about how we can solve this problem. So I'll be just back in 2 minutes. So anyone has any idea of how to solve this problem?
we have to express this in the form of y is equal to phi theta form. That is the
Yes.
and then we can solve for the parameters matrix, that is the theta vector.
Right. Exactly. Yes. So we can write this in basically the y is equal to phi into theta kind of form. So here our theta will be basically a and b, and our y vector will be 3, 8, and 7. So this will be our phi matrix. So our least square estimate of theta will be basically, it will be so is this the correct equation?
Yes, sir.
Yeah. So so we basically just have to calculate first phi transpose phi. So maybe we can take 2 minutes to work out this.
Okay, okay, I think we can do this calculation, sir. Can we go forward?
Yeah, we can go forward. No problem. So the next question is, this ident toolbox is used for analyzing what? So ident here means basically system identification toolbox.
Both.
Yes, it is both, analyzing both the input and output signals. So the next question is, black box in system identification. It is used to
B, answer B.
yes, it is correct. So in black box, we do not know what are the physical relations between input and output. So we cannot derive the model from laws. So we need to choose some standard model and then tune the parameters to that model from the data. Now this question is with respect to optimization. Geometric constraints are useful to define what?
Both A and B.
Yes. Yes, we can define the upper and lower bounds using the geometric constraints. Then the next question is graphical method is used when we have a problem using how many design variables?
Two design variables.
Sorry,
Two.
two design variables. Yes, exactly. So we can use graphical method with two design variables.
What method will be used when we have three design variables?
Then graphical methods will be slightly difficult. Then we can use other like methods like simplex method. So if we are having a linear programming kind of a problem, but in three design variables, then we can use other techniques like simplex method. Or if the problem is non-linear, like if the objective function or the constraints are non-linear and we have more than uh, two design variables, then we can resort to other uh, like non-linear optimization techniques. So, so we can either use directly inbuilt solvers in MATLAB, or we can, write our own algorithms. So depends on the problem basically. But this graphical method is, restricted only up to two design variables, because planar, like we can visualize things in a plane easier, but in three dimensions it's very difficult to visualize.
Okay, sir. Thank you.
Then the next question is about golden section method.
Multivariable.
No, actually it is applicable to only a single variable.
Okay, golden section. Yeah, fine.
Yes. Yeah, so the next problem is if the search interval is 0 to 3, so if we use successively this golden section method, uh, find out the interval of uncertainty after the fourth iteration. So when we say interval of uncertainty, it means basically the difference between the maximum and minimum values of the interval. For that, how do we solve this?
uh, that difference between the max and the minimum and the some factor will be taken, like some 0.6 something will be there for every iteration. It will come down that. Not able to recollect exactly.
Yeah, so there was a a formula that was given in the slides. So where we can actually just apply that formula here. So the interval of uncertainty in the nth iteration, it is basically the initial interval into this factor of 0.618 raised to n minus 1. So it will be basically 3 into 0.618 raised to 3.
What is this? I0 is maximum minus minimum.
Yeah,
Okay. So It is if it is a 2-3 is the interval, you'll be putting it as a 3 minus 2 and hence only 1 as I0.
Yes.
Okay. Okay. Thank you.
So what will be the answer?
Around 0.7.
Yeah, it's around 0.708.
In general, sir, in NPTEL courses,
Yeah.
they share the lecture slides,
Yes.
but somehow this course, the slides were not shared. And now, towards when are coming close to the examination, it is becoming a little difficult to go through all the videos and whatever pictures are there in the transcripts files, they are not visible, clearly visible.
No, the lecture slides are there already, right? So we can access the lecture slides.
So
No,
the
there
video
was
slides, if you click on, it will open a Google, download it, or you can take a print of it, or you can save it.
no. I have not seen it in the course page anywhere.
No, let me just show you. Let me just show you. If that is the case, let me just show you. Just a minute. So I am sharing my screen.
Okay.
So are you able to see it?
Yes, sir.
Yeah. So this is like the week wise
Right.
thing. So like when we go to each lecture, so there is this
Oh, okay,
this
okay.
thing
Below.
below
Okay, okay.
where we can see the lecture slides. So we can view it here itself, or if you want to save it, you can go to this pop-out window. So it will open up this as a Google Drive link, and then here we can just download it.
Okay, sir. Okay, okay. I was watching them all the videos in the YouTube, and when I click on that link, I was seeing the video and I have never scrolled it down.
Okay.
Looks like they have changed the format.
Okay.
Okay, sir. Thank
So
you.
you will be able to access, I think, the lecture,
Yeah, yeah. I
lecture
am able to
slides.
see them.
Yeah.
Okay, sir. Sorry for
Yeah.
earlier. They were providing a link under after the lecture names.
Okay. I think they keep changing
In other
the
courses.
course in like interface from time to time.
Okay, maybe. Yeah.
We just
Option C.
option C. Okay.
Just multiplying x1, x2, x3 with the profit rupees.
Yes. What about the others? Anyone has any other answer? So the correct answer is C. Yes, 3x1 plus 2x2 plus 4x3. We just have to multiply the uh, profit per item into the number of items to get the objective function for maximizing the profit. So now we have another problem where we have parts manufactured by different machines. So we need to formulate this problem and solve for the optimum number of parts 1 and 2 to be manufactured so as to maximize the profit. So I'll give you a minute to go through the problem. So we need to find out the optimum number of parts 1 and 2 to be manufactured per week. So let us assume the number of parts to be manufactured for 1 as x1 and let us assume this as x2. So what will be our objective function now in terms of x1 and x2?
X1 plus 100 extra.
Sorry?
50x1 plus 100x2.
Yeah. Yes, it will be 50x1 plus 100x2. So that will be our profit. So since we have only two variables, so we can solve this problem graphically. Now the next step is to identify the constraints on x1 and x2. So like if there were no constraints on the maximum time available per week for each machine, it would be infinite number of x1 and x2 items, but that is not generally the case in reality. So we introduce these constraints. So the first constraint would be what? So it will be basically the x1 and x2 are positive. And then the next constraints would be basically based on the maximum time available per week for each machine. There is some problem with the screen share. So then the next constraint would be basically for lathe, the maximum time available is 2500. So the machining time required for part 1 and part 2 together, so will be basically
10x1 plus 5x2 should be less than or equal to 2500.
yeah. Yes. So similarly,
4x1 plus 10x2 less than or equal to 2000.
yes.
And then x1 plus looks like 1.5x2 less than or equal to 450.
So we can plot these equations on a 2D plane, because the constraints are in two variables, and and the objective function is also in two variables. So we can plot these lines using the x and y intercepts. So for the first constraint, if we put x2 equals
250 comma 0, 250 comma 0 to 0 comma 500.
yeah. So
We have put the first equation x equal to 0, y equal to 0 and got the x value. And similarly, we have put x equal to 0 and got the y value.
yes. So now if we join these 2 points, so this is our constraint 10x1 plus so it will be basically less than or equal to on this side. So this is our allowable region. So the arrows indicate the allowable region. Then for the next constraint, 4x1 plus 10x2.
We put x10 we get 200. You put x20 you get 500.
Right.
Can you copy those constraints onto this page?
The Google Jamboard interface is not so user friendly.
Okay.
That's why I have
Okay.
to, flip between the slides.
Okay.
Unfortunately, I could not figure out a better tool, but maybe for future I can try to find out. But as of now, I have to live with this.
The Zoom meeting, maybe it comes for only 45 minutes, but it has a lot of tools to write on the board.
Yes, yes. No, since this we had a constraint on the, the with our institutional subscription, we can get this unlimited time, but it was available for me only with Google Meet.
Okay.
200.
Similarly, with the other constraint, so we have x1 is equal.
That was not 400, sir. It is 0, 200.
Sorry, sorry. So it will be actually somewhat flatter. Then the third constraints. So even in this case, uh, so
450, 0 to 0, 300.
so this is just like just a rough kind of a sketch, but for exact plots, like we can actually just go to MATLAB and plot the each line of the constraint. So then, in order to avoid such mistakes, like the region, the shape of the region that we see may be slightly different. So then, what we can do is we can just go to MATLAB and plot the constraints there itself. So let me just do that. So our objective function f was basically 50 x1 plus 100 x2. So our first constraint was basically so our first constraint was basically 10 x1 plus 5 x2 is less than or equal to 2500. So we can rearrange so in order to plot it, so we can rearrange it as x2 should be less than or equal to 2500 by 5. So it will be 500 minus 2 x1. The other constraint was 4x1 plus 10x2 is less than or equal to 2000. So then we can rearrange this to x2 should be less than or equal to 200 minus 0.4 x1. So we assume a sample like interval 0 to 750, or we can actually reduce it to 600 also, so as to visualize the constraint lines. And then the third constraint x1 plus 1.5 x2 is less than or equal to 450. So therefore x2 should be less than or equal to 300 minus 2 by 3 x1. So here we get the plot of all the three constraints. So now then we can put a limit on the value of y from 0 to, because we do not, we will discard the negative values. Yeah, so now we get the value of the like the intersection. So on the lower side, like which, to find out which side of the constraint is allowable, we can substitute the value of the origin in the equation. So like for each constraint, let us say if we substitute x1 and x2 are both 0, then we'll get 0 is less than or equal to whatever value on the right hand side which is positive. So therefore the like the side below the constraint line is the allowable region of the for each constraint. So therefore in this case, now if we look at the intersection of all the three constraints, we can see that this region is the actual feasible region. So the third constraint has actually no role to play in this case. So because the intersection region is actually smaller, and even inside that constraints region. So now generally the solution will lie at the corner points for a linear programming problem. So then
Does
the
this happen, sir? Does this happen at every time that one constraint will become redundant?
not necessary. Now suppose if this constraint was like somewhere, if this constraint line was somewhere below, like let us say if it was something like, you know, less than or equal to, instead of less than or equal to 450, it was something like less than or equal to 250 or something like that, then the constraint line would be slightly different.
Okay, okay, sir.
So yeah, so it all depends on the problem. But so here we can see graphically that, you know, this point of intersection, so that which is the corner point, so the solution point will be somewhere near this intersection point, which is about 186.7 and 125.3. So there are three corner points possible, either 0, 200, and then the third point will be this 250 comma 0. So we can check the objective function value for each combination. So let us say, and see what will be the profit. So it will be basically 50 into 50 into 0 plus 100 into 200. So that will be basically So that will be the profit for the first corner point. Then for the other corner point, which is 250 comma 0. So it will be 50 into 250 plus 100 into 0. And the third corner point will be 186.7 and 125. To 1865. So the profit value is actually greatest for this corner point. So that's why the optimum solution will be this corner point. In some cases, it may happen that one of the corner point where one of the design variables is 0 is also the optimum solution, but in this case it is not so. So this is how we can solve this problem graphically using MATLAB.
Maybe you should use a Desmos. Desmos would be much better one.
Sorry?
There is a tool called Desmos. If
Okay.
you use it, it is much quicker than MATLAB, at least for this problem.
Okay.
Desmos is a graphical calculator. DESMOS.
I see. I was not aware of that.
Okay, no problem. No problem. Just plug in the equation. It just plots it.
Okay. Sure. Then I'll try it out. Thanks.
Okay. Okay.
So then
You stopped your screen sharing.
yeah. I'll just share it back. So now I have another similar problem, which is a linear programming problem. We can solve it graphically. So we can use again the similar way of using MATLAB here.
Shall we do it in Desmos? It's very easy.
Okay, I'm actually not familiar with this.
I can show you. If you want, if you're going to do it on MATLAB, I would say that let us do it on Desmos. If you want to give this as a homework, I'm okay. We'll move on.
Yeah, maybe if time permits, we can try it out later on with
Okay, no
that.
problem.
I'm actually not familiar with that particular tool.
Okay.
I was actually again going to go to MATLAB for that.
I think we can solve this at our end. Maybe you give the final answer if you have it.
No, I don't have the final answer with me.
Okay.
I'll also discover the final answer along with you only. So yeah. So if you want, we can then go through the problem, or like we can just move to another problem. So I have now like set of like such 2 3 problems where we can use either MATLAB or whatever tool to solve these kind of problems. So I have another problem like this where we have now non-linear objective functions and non-linear constraints, but we can still solve it graphically because it is a two 2D kind of problem. So I suggest that we can try this example with the non-linear functions and constraints in MATLAB, and then I think the linear problem we can actually try with that Desmos thing.
Is this the end of the one, or you have further some more questions?
No, I just have these 2 questions.
Okay, sir.
So I suggest that we can try out this example in MATLAB.
In MATLAB, it is taking 10 to 15 minutes time, whereas in Desmos, it takes less than 2 minutes
I see.
because you are trying to enter everything, format it.
I see. Okay. Fine. I
Any
think
of
the
the certain
yeah, I think the next problem we can try out with that. Or else if you are able to share your screen, we can
No, I
actually
can tell you if you can open Desmos screen, I will just show you. Go to www.desmos.com. It's very easy.
okay. So yeah, this was the problem.
Okay, go to desmos.com.
Yeah.
Open the graphical calculator.
Okay.
Okay, in that box, kindly paste that equation, whatever is your constraint. Minus x1 plus x2 less than or equal to 1. You have to put it in terms of x and y here because it doesn't recognize x1 and y1. Minus x plus y less than or equal to 1.
Oh, okay.
Put the next equation.
So I have to do enter.
Yeah, that's all.
Okay. Wow, nice. Oh,
So very okay. Put the next equation. Minus 2x1 plus x2 minus 2x plus y less than or equal to 2. Equal to less than or equal to 2.
okay.
Equal to just that. No, maybe instead of putting that, let us stick with only those two. We know first two only. So now we can see that you click on that, it gives the intersection point.
Okay.
So we know the intersection points, and we also know the objective function.
Yeah, so the objective function is 2x1 plus 6x2.
Put it as some g equal. I am not sure it will take on that. Put it as some g equal to
G equal to.
g of xy. I'm not sure it will take or not. For one, put it as g of xy. Maybe once we get these intersection points, we have to do it on Excel or something because yeah, test taken. Okay, now whatever intersection points you got, put them as g of in the next one. You got intersection points, right? G of values 0.333, comma.
Okay,
You see,
so
it has
this.
given you the value.
Okay. So it calculates the objective function value also. Okay.
Yeah, you can put the next whatever
Corner point.
points
Yeah.
again.
Yeah. So 1, 0. So it's 2. And then for this point, it is 0, 1. Yeah. Okay. Great. So yeah, it's indeed very easy to calculate with this tool. Thanks.
It's a beautiful tool. Kindly explore. It will help you a lot when you are teaching students.
Great. Yeah, thank you very
It
much
does.
for sharing this.
Okay, no problem.
I was not aware of this tool.
Someone like you has told me. Okay. So our answer now is going to be 6 for a 0 1, right? Or no, I'm not able to see.
Yeah, so this will be the corner answer will be this corner point, 0.33 and 1.33. So then we can also try the other non-linear problem also with this graphical.
If you click on that X mark, that equation will go off. Yeah.
Oh, I can actually save also like this graph. I can.
Right. Right. You can save it. It will stay in your Google Drive forever.
I see. Okay. Okay. Fine. Interesting. So now we can define our f
Let's
as
try this.
f of x comma y is.
F of x y equal to x square y square, something like that. Right? X comma y equal to x square. Yeah. Okay.
So f of.
You code below, you can directly then, it's very easy.
Yeah, so then it just plots the constraints by itself.
I don't know whether it will recognize. You have to type some e equal to 2.71. I don't know whether it takes e there. Two 2.71. That should be 2.72. Should be fine, right?
Yeah.
No, not 2.72 should be fine. Okay.
So it doesn't know the value of e.
Oh, okay. Fine. It is taken. Sorry.
Yeah, so it has already plotted us two curves. Yeah, it's indeed very easy.
Okay, so now maybe next to the E, if you want to see only the values in the first quadrant, next to the each equation, you type open curly bracket. Next to that each inequality constraint,
Mhm.
open the curly bracket and type there x greater than equal to 0, comma y greater than equal x greater than equal to 0, comma y greater than or equal to 0. Close the curly bracket.
Curly bracket. Okay.
It has not taken. Yeah. Okay. Now copy that constraint in all the three equations.
But it still
It has
plots
not
the
removed.
other quadrants.
Yeah. Maybe it is instead of comma, can try semicolon. Have you put x and y? It looks like you have put only x. It is comma. Okay. I don't know why it is removing it. It's a comma, right? Comma or semicolon? I'm not sure.
Comma.
It's giving some error there.
Or should be and or something.
Okay. N, I'm not sure.
No,
I have
and is
to
not.
check.
I don't know. Maybe it's some other character.
Yeah. Mm, that's not will be multiple constraints.
Yeah, but I think basically now the intersection region is only this thing, which is the purple between that blue, green, and purple is only this thing.
Maybe put them in separate curly brackets. It may work. Yeah. Okay. So the intersection, put them in separate curly brackets. Is it coming?
No.
Leave it there. I don't know. Sorry.
For now, we can just zoom into our region of interest. So
Okay.
here also we can just simply set the x-axis and y-axis.
ते छोटे रेडिओ दोन्ही ते हिटिंग पॅड त्या इलेक्ट्रिशियनच्या दुकानात घेऊन जा ते दुरुस्त करून आण.
So our intersection points, is it able to locate here in this case? I don't think so.
त्याला तू घेऊन ये
Yes, sir. You just click it. You just click it. It will give you.
काही
Click at the intersection point. It should give you. So it has given earlier, right?
It gave earlier, now right now, but it's not giving for some reason. I don't know.
I'm not sure. Maybe it is because of.
लेक्चर वाढवू नको रे पार्थाचा.
But yeah, basically the corner points, what we can see is like the feasible region looks like only this much, this. Only this patch, which is between here. So the optimum solution is somewhat, I think, around like 4 comma uh, 0.55 or something like that. So So that corner point. So that looks like the only solution. But yeah, it's a
On Google, he was showing it as a he's showing it as an putting them in two separate curly brackets. X greater than 0, curly brackets closed, and y greater than 0, curly brackets closed, open and closed.
so there needs to be a comma in between.
No comma. Close the curly bracket after x greater than 0 and open a curly bracket again. Yeah. Is there a comma between? There is no comma, right? It has taken the first one. Okay, it has taken the second one.
Yeah, it does take. Yeah, it does work that way. So the
Only thing
intersection.
is, it is not giving us.
Sorry.
It is not giving us the intersection points, I think.
No, I think it's not able to locate the intersection point here. But anyway, we can approximately say that it's around 4 comma
One.
4 comma 0.55 or something, and so
Okay.
that will be the only corner point. So that, and our problem was to minimize that. So it will be basically point 4 square into 0.55 square. So that will be our so 4.84 will be the objective function value.
Okay.
So yeah, so that's all that I had from my side for today's session and for this course also. So I hope all the sessions that we had till now were useful.
Give me the feedback.
So I request all of you to give me feedback. So you can actually just write to me directly also. So I'll give
Okay.
you my email ID. So I have shared my email ID in the chat. So if you have any feedback or any questions so please do share your feedback. So you can just directly email it to me also, no problem.
Course,
So for your entire,
how was it? Useful, utility.
so that's all that I had from my side. Hope you have
Enjoy.
hope you enjoyed the course and hope you learned well and I hope all the online problem sessions were also useful. So do let me know what do you think.
Okay, sir.
So all
Thanks a
the
lot.
best.
Have a nice day.
Yeah, thank you.
Yeah, thank you. Yeah, yeah. I have one final question.
Yeah, please go ahead.
Yeah, regarding the exam part, the pattern of the examination will be like how many like it is mentioned that it is for 3 hours.
Okay,
And because this is the first time I'm writing at an NPTEL exam,
I see.
so it would be like multiple choice questions for for 100 marks, or like how it would be.
It would be a subjective exam, I suppose.
Okay.
I'm not really sure about the exam pattern, but I
Okay.
think it may have some part of multiple choice and some part of like subjective
Okay.
questions.
In general, all FPTL are only objective type, except they are mentioned in the course page. Maybe if you see the announcement page, I think very recently they should have sent an email regarding the exam. In general, they're all objective type. Okay, you'll have multiple choice blanks, multiple select questions. Most of them will be from uh, related to our quiz questions. Uh, so if you do review the quiz questions, and I think the online sessions, I think we should be getting a very good score. That's how these sessions work. They will be giving some questions which we have not seen earlier during in our assignments, but they will ensure that a student who has worked well on the assignments on his own and attended the online sessions, they'll be able to get good marks.
Okay, so it's not
Regarding
involved
subject,
lot of multiple choice, is it?
it will have multiple choice, blanks, multiple select questions.
Okay,
In general, they will be. You will also have blanks also where we need to just answer the number.
I see. Okay.
Okay.
It will be similar to our assignments. Whatever we have done
Okay.
on the assignments, it was similar.
Yeah,
But
understood.
I don't think I have seen a. If it were a subjective, then the assignments would also have been subjective. They would have given some subjective questions in the assignments also. Since that is not the case, I don't expect any subjective questions in the final examination.
Okay.
Okay.
And I think they have sent an email regarding format, exam format 2 days back. That would be a general email for all the exams. But again, saying since we don't have subjective questions in the assignments, I'm not expecting any subjective questions in final examination.
Okay.
Not to, I don't. Some of the keyboards in the examination center will be horrible. I hate them. So it would be better we have only multiple choice, multi-select or fill in the blanks. They will
Okay.
provide you they will provide you rough papers where you need to work on. No your online screen will also have an online calculator where you can make use of it to do your calculations. And at the end of the examination, they will collect back your sheets. You're not allowed to. All those instructions will be there on your hall ticket. You have to carry some ID proof without which they will not allow you into the exam hall.
Okay.